Hello, good morning, guys. So this is the standard that we're going to be working on today. Again, if you want to use the standard into CPOMs, just type it in with the letters and numbers, and then you can get access to the student original tutorial for it to help you out also. So for this specific standard, we're going to be recognizing the light waves, sound waves, and other waves move at different speeds in different materials. So when you think, oh, also, if you do have the textbook, you can go to topic 2, lesson 1, pages 42 to 49. All right, so types of waves. So when you think of a wave, you probably picture a surface wave on the ocean. So actually a wave is any disturbance that transfers energy from place to place. An ocean wave is one type of wave called a mechanical wave, meaning it moves through some type of matter. The matter of a wave travels through what is called a medium. A mechanical wave cannot pass through a vacuum, such as space. Sound waves are another type of mechanical wave. Sound can travel through the ocean, but it can also travel through a solid object, such as a piece of metal or a gas, such as the air. It cannot travel through a vacuum, such as space. So remember, a mechanical wave has to be traveling through something. So that's why sound is a mechanical wave, because if I'm screaming out in the middle of space, no one's going to be able to hear me because there's nothing there. It is called a vacuum. There's nothing there. There's no air molecules. There's nothing. So nothing can be vibrating to make you hear something. Another type of wave is an electromagnetic wave. This type of wave transfers electromagnetic radiation, a type of energy. Examples of electromagnetic radiation include visible light, radio waves, X-rays, and microwaves. Like a mechanical wave, electromagnetic waves transfer energy. However, electromagnetic waves are unique in that they can travel through without a medium. Both types of waves involve a transfer of energy without a transfer of matter. While mechanical waves travel through matter, the waves themselves do not move the matter to a new place. The waves are disturbances in matter that transfer energy. So ocean waves cause the bob in the water. So that thing that you see in the middle of the ocean, those would be moving. So if the seafloor sensor detects a wave called a tsunami, for example, it's going to send the signal to these floating bobs. Then they send a radio signal to satellite orbiting Earth. The signal gets relayed to scientists who can then warn coastal communities. The sunlight that lights this scene is also made of waves. So anything that's coming from the electromagnetic spectrum pretty much is going to be transferring energy. The thing is that some can be transferred through a wave, and those can be, and some of them can be used without a medium, or not through a wave, with a medium. All right, so transverse waves is just a type of wave. So waves can be classified by how energy is transmitted. Energy is transmitted through a medium by mechanical waves. Electromagnetic waves are capable of transmitting energy through empty space. Waves can also be classified by how the particles in a disturbance vibrate. A mechanical wave begins when a source of energy causes a medium to vibrate. The direction of the vibration determines what type of mechanical wave is produced. A transverse wave travels perpendicular, so at right angles, to the direction of the source's motion. The person that you see right here, these little people right here, is using his arm to make up and down vibrations in two ropes. Each particle of the rope moves up and down. The direction of the waves he's producing, though, is perpendicular to that up and down motion. The energy travels towards the far ends of the ropes. The curved shape of the ropes indicates the main features of a transverse wave. The high point of a wave is called the crest, and trough is the wave's resting, is at the bottom. Halfway between the crest and the trough is the wave's resting point. The distance between the highest crest and the resting position marks the wave's amplitude. In general, the amplitude of a wave is the maximum distance the medium vibrates from the resting position. So electromagnetic waves, such as sunlight, are also transverse waves. In their case, however, there is no motion of particles, even when light travels through a liquid, such as water, or a solid, such as glass. So again, we have our wave here. This dotted line is going to be our resting point. So it's halfway between our crest and our trough. So our crest, remember, top of the hill. So at the top of these waves is going to be our crest. At the bottom, we have our trough. Then we have our amplitude, which is from the crest to the resting point, or the trough to the resting point. So just from the top to the middle, or for the bottom to the middle. Okay, I would definitely draw these out on a piece of paper. Make sure you have them somewhere so you understand what it is. So remember, trough, it's not that the wave has one trough. Every time there is a dip on the wave is going to be called trough. Same thing as crest. Equilibrium is also another word for that resting point. And then we have our wavelength that is from crest to crest, or you can actually measure it from trough to trough as well. We also have these longitudinal waves, different type of wave. So a wave that travels in the same direction as the vibrations that produce is called a longitudinal wave. So sound is a longitudinal wave. Sound travels from speakers when flat surfaces inside the speakers vibrate in and out, compressing and expanding the air next to them. This longitudinal wave in this particular picture is like a spring toy. So when the left hand pulls on the toy, the result is a series of stretches and compressions. Gaps between compressions are called refractions. Energy moves in the right along the toy. While the wave travels, the spring particles do not move all the way to the right like the wave does. Each spring particle moves back and forth like the hand. The small piece of ribbon on the spring moves the same way the particle as the spring moves. So if you want to think about it, this would be like a slinky. Okay, so we have these different waves. Just know that it is moving from, you could say this way to that way, this way to that way. It really doesn't matter. It kind of just matters where these compressions and these refractions are. So all these areas where you see that there's more, that they were closer together, would be a compression. So remember, compression is just a term that means to be together, it's close together, to be pushing something together. And then these would be your refractions, where it is not so tightly commed in. All right, so our surface waves. So combinations of transverse and longitudinal waves are called surface waves. For example, an ocean wave travels at the surface of water. When a wave passes through water, the water and anything in it vibrates up and down. The water also moves back and forth slightly in the direction the wave is traveling. The up and down and back and forth movements combine to make each particle of water move in a circle. So this is what they're talking about. So this ball, for example, is going to be moving up and down because the waves are passing by, but it's also going to be moving in a circular direction because there's also these ripples. So yes, they are moving, but these ripples are also going to be pushing it up and down. So this up and down motion and this side to side motion is going to be creating this elliptical trajectory, or this just circle movement of something that's floating. So in this particular scenario, we have a ball, but that's why most of the time things stay in place in the ocean, unless, you know, the currents are extremely rough or anything like that. But they're going to kind of float up and down, side to side a little bit, but they're going to be spinning. So waves have many different properties, like we've already talked about. So in addition to amplitude, all waves have three other properties: wavelength, frequency, and speed. These properties are all related to one another. So for wavelength, suppose that a wave repeats as it travels. So if its wavelength is determined by the distance it travels before it starts to repeat. So the wavelength of a transverse wave is the distance from crest to crest, as shown in this figure right here. For a longitudinal wave, the wavelength is the distance from one compression to the next. Okay, so you could do the wavelength like we've already said. So it has to be from crest to crest. Also, you can also do the wavelength from trough to trough. It's just, you have to do it from two specific points at each wave. So it has to be the same point on two different waves, or on the same wave, sorry. So longitudinal will be compression to compression. So remember, if you're looking at a slinky, anytime that they has a compression, so anytime the slinky is very close together, you're going to measure from that to the next one, and that would be your wavelength. Frequency, the number of times a wave repeats in a given amount of time, is called its frequency. You can also think of frequency a number of waves that pass at a given point in a certain amount of time. For example, if you make waves on a rope so that no one passes by a point every second, the frequency is 1 wave per second. Frequency is measured in units called hertz. A wave that occurs every second has a frequency of 1 hertz. If 2 waves pass by in a second, the frequency is 2. So whatever it is, so for example, if we're looking at these various waves, let's say, for example, this is considered 1 second. So let's say we're looking at this green one. So we can say that there is a frequency of 2 for this green one, because if you're looking at it, here is one wave, it stops here. A full wave would have to be from the resting point until you have a crest, a trough, and you go back to a resting point. So it'll be 1 wave, and then you have 2 waves, or 2 hertz, because it's measured in hertz. That would be your frequency. Now, if we're looking at this orange one, we have our crest, our trough, bam, we have only our crest. So that will be considered a 1.5, okay, in that second. Now we have our red one. So we have, here we go, this is 1, this is 2, and this is 3. We got 4, 5, 6. So we have a frequency of 6 hertz in that 1 second. Speed is another measurement that's very important for waves. The speed of a wave is determined by the distance it travels in a certain amount of time. So different waves have different speed. For instance, a light wave travels almost 1,000,000 times faster than a sound wave travels through air. Waves also travel at different speeds through different materials. For example, light travels faster through water than through glass. Sound travels more than 3 times faster through water than through air. To calculate a wave's speed, divide the distance it travels by the time it takes to travel that distance. You can also find a wave's speed if you know wavelength and frequency. Just multiply wavelength times its frequency. So sound travels a lot faster in water, okay? So it travels 3 times faster. So this is why it's very easy for animals, let's say dolphins, whales, things like that, to communicate underwater, because sound travels so much faster in water than through air. So again, we have this 1 second. So, oh wait, let me go back. This 1 second. So if we're looking at, let's say this is wave 1, wave 2, and wave 3, we can tell that the highest speed, for example, is going to be, remember, speed is directly, what's it called? Directly related to frequency. So this 3 is going to have a higher frequency, so it's going to have these more waves during this 1 second period, so it's going to have a faster speed. So this one, the fastest, then we have our number 2, the fastest, and then our number 1, so just make sure you know that. So for here, we're going to pause. I will be posting the lesson check questions on Thursday, so just look out for that. All right, thank you.